if we start with the tour, then what I did is I've got little boxes to keep all our little components in, little plastic boxes. I had them made at a company in town. They cost a few euros each to keep all the little components safe and nicely packaged. One of the projects that we're working on is to make optical fiber sensors. So we're working with the geologists. This is actually a geophone. So this is a 3-axis accelerometer geophone, and this will be buried in the ground and then measure slight ground tremors and vibrations. This is the battery pack. So one of the things we do is we make sensors, fiber sensors, using interferometry, coherent sensors, polarization. Really, the challenge is to make optical fiber sensors with better performance than these big devices. And here you can see one of the students has James, who's doing his PhD. He set up this tank, and it's a tank to investigate sinkholes. So he flows some water through the tank, and then we have some fibers running, and then it's like detects the different stages in the sinkhole collapse. Here with the sensors, we measure in the resonance of this water it's water tube, this tube, using a speaker. So it's something we're measuring with our sensors. Underwater robots. So within that project, my job is to do the communication work package. So the communication between the robots, from the controllers to the robots, and also from the data and center, from the data packs and sensors back to the ground. So this is a flying robot, right? But it's one that we take apart and think how to make it into an underwater robot for underwater communication. We have some polarimeters from Adaptive. I think these are fairly old units from Ralph Stalter's company. Moving along, we have a WDM laser rack. We have this old equipment that you would have seen when you visited in 2007, I think. This is some dispersion measurement equipment. We don't really use that often. Coming across here, we have a 10 gigabit bit error rate tester, an harmonic EDFA. This bit error rate tester is from the company Lucio. It's a German company. And recently we actually got an upgrade. So this is the 100 gigabit per second version. It has 4 lanes of 25 gigabit per second. Then we have a Fotline modulator. So this is one in the box. This box has an intensity and a phase modulator. It operates up to 40 gigabits per second. We have a lot of little components. Let's see, what's this? This is a Discovery semiconductor photodiode. The way I've packaged it in this plastic box, but it's also got some protection circuitry and components that we've included. So when the device gets blown and the students connect the wrong voltage, at least there's a little fuse and a Zener diode to protect it. I remember we once had a discussion about the trade-off of having individual components like this that can easily be damaged but are really nice to learn on and to teach the students on, versus something that's just a black box, which is more easy to operate and more robust, but it's not always like didactically that good for the students because they don't know exactly what's happening. We have the VCSELs, the Finisar board, the 1310 and 1550 VCSELs, some diode controllers, power meters. Here we have an NKT laser. So this is a narrow line width coherent laser that we're using for our coherent sensors, and also for timing distribution timing and reference signals over fiber, and like a phase stabilization. Of course, we have some all the traditional power meters. Here we have our scope, our high speed oscilloscope, and we have a coherent receiver from Discovery Semiconductors. Each year I've kind of applied for funding, different grants through the government, South African government. I'm doing some projects with South African industry, so I've been fortunate to raise funding to get equipment over the years. We have some multi-mode fibers, some multi-mode VCSELs and photodiodes from Raycan. Coming over this side, here we have a low-speed Tektronix oscilloscope, and as I said, this is we're interested in the underwater communication. So I have these two lasers in this free space configuration, and then we put in water in the signal path, and we add in some bubbles, and here we have the students been measuring out some cool drink, which we're using as color in the water tank. And then we're seeing, what effect does the turbulence and the coloring of the water have on the signal channel, and how to correct for that, perhaps using machine learning and other techniques. Our students, they're good at building little circuits, breadboards. We have just an OSA optical spectrum analyzer. We have the national instruments, for writing little scripts during the digital to analog conversion. Here we have more. I think this is just another photodiode with the fuse and the Zener diode protection. This is a nice little stack of equipment. This is what we've been using for our time and frequency distribution. So that's been for Meerkat, for SKA telescope. We have a Stanford's Instruments rubidium clock, which we've bound to the signal generator, which operates up to 20 gigahertz. So the frequency reference makes sure that the sine wave is stable, and then we have a spectrum analyzer up to 20 gigahertz, which we can measure the noise, the Allen deviation stability, and so forth. We have lots of like RF components and RF amplifier, just like you had for us in Denmark. I think this is you recognize this. This is the NEL DFB. Again, just some temperature controllers. Oh, here's the little water tank we were using for the underwater robotics communication experiments. Some equipment from VCSELs from Raycan, photo receivers from Raycan. We have some OFS fibers. If I take you this side, we have a whole lot of RF components, splitters, couplers, filters, mixers. That's one of the things we've been using for our phase correction to create error signals, and then a phase lock loop. So we create the error signals through using mixing. Coming over this side, we have just the normal splicer, some more spools of fiber, an OTDR. Moving this way, it's just a bunch of equipment. There's a very nice antenna company called Pointing. They're a South African company, and they make a whole range of different antennas. So I've started a project working together with them and become a little bit more interested in wireless. I remember in Denmark you got me interested in working on the ultra wideband communication. That was really something interesting to get me into. But now moving on, let's have a look at this antenna. This is an antenna that actually goes on top of a a truck or a car, and it's really a wideband antenna, a directional antenna. Just a bookcase. This is the wall that we write all our ideas on, and it has these words above the wall where we should dream, create, inspire, and achieve. And then whenever the student has an idea or we want to discuss something, we're able to just go to this wall and write our ideas on the wall. And I mean, when we're young, our parents tell us not to write on the wall, don't make a mess. But actually, it's cool to be different and to actually write on the wall. In this area, we have a relaxation area. It's a little room, and you can see there's a comfortable couch. There's a TV and some computer games if the students want to play games. We have a kitchen area where they can make some food. And then we also have a robot vacuum cleaner. And I got this robot vacuum cleaner just to remind the students that, really the computers are coming for your jobs. We need to innovate. We need to be different. I'm going to take you into a room next door. And in this part of the lab, the part we're going to visit now, we have Cisco ROADMs, and we're interested in, WDM ROADM experiments where we're using machine learning and colony optimization to optimize routing. Let's take a look at that. It's a little noisy. So over here we have Josh. He's busy doing experiments, and if we take a look, you can see we have 4 ROADMs, and then transmitters and receivers in a northeast southwest configuration. And Josh is busy implementing his machine learning algorithms on this computer to control the hardware.